Yo, yo, yo. Welcome back. Today we're working on my Rust operating system for x86. It's not doing anything crazy right now. It's like basically just a demo kernel that boots in QEMU. It loads, it sets up a memory allocator, logs to serial and VGA, like has the ability to run some unit tests, read the clock, work with PCI, and we're starting to get to the point where we can like work with Ethernet a little bit, and has like Rust async support built in. So this is like the demo where like here's the VGA device, which would be a monitor, and here's the serial output, and we can see like we have logging set up. We're changing the clock, so here we have like 21 hours. Then we change the time. We have 20 hours. Great. We can like read the MAC address from the network card, and we can like sleep for some time before we exit later. So pretty cool. Yesterday we got pretty far. We were working on our network driver, and we kind of got like this stuff done. So we like got our driver stubbed out, and we kind of figured out how to like work with the memory mapped RAM, and we figured out how to like initialize the card and start trying to transmit data. And where we got stuck is on initialization. We were trying to pull the interrupt number from the PCI device. So if I just pop open the little diagram here, we can kind of like show how this is connected. So we have this is my CPU where the code is running, and there's memory controller, mem. This is like in hardware. We have like RAM lines connected here. This is like where our reads go, and this will go to like the RAM stick here, right? You have like a few of these. Maybe we'll draw like a couple, right? Like four gig sticks or 16 gigs of RAM or something. This line is also shared with like an IO controller, which is like basically does the same thing as memory, except we have to like switch between them. So if we say like go to address like 50, that could go to like the memory controller, which would then go to RAM usually. Or we can say like, hey, no memory accesses right now. We want to pull from the IO area. And so this will be connected to like serial, or in our case, PCI. PCI, where PCI is just like those slots for like your GPU and shit. So what we have here is we talk to PCI to figure out like where the Ethernet card is. So this guy, my Ethernet card is plugged into the PCI slot. So ETH for Ethernet, not for crypto. And then here, this guy's also connected to memory and is connected to IO as well. And so what we do is we start by like doing like a little read to PCI, and we say like, hey, how do we interact with you? What are the rules for talking to this guy? And he'll say like, oh, here he's at memory address like 10, and here he's at IO address like 50. And so we can like talk to these guys through these addresses and like put data on here. And what's supposed to happen is we are going to like send some data onto the card. So we have like send some data is wrong. We're gonna like put some data into RAM, and then the Ethernet card, we're gonna tell the Ethernet card like, hey, time to do some work. Like here is where that RAM is. So he'll like talk to him, and he'll start transmitting this guy, and that can take some time. It's not like instantaneous. It's something like we have to wait for the data to get out. And so what happens is we would like to know, how do we get the data off the ether? Like, how do we know when it's done? And so you could like sit there polling a register on the Ethernet card saying like, oh, when are you done? Are you done yet? Are you done yet? Are you done yet? Are you done yet? But he's going to like that. Then your CPU can't do anything else unless you're like preempting that loop with something else. And what I'd prefer to do is talk to this guy through interrupts. So there's also this other line that goes to the CPU. called the something interrupt controller. This guy's hooked up to him. He's hooked up to the CPU. And when he's done, he'll be like, I'm done now. And this will come over here and be like, he's done now. And that will like interrupt whatever I'm doing on my CPU. And now my CPU goes like, oh shit, time to put more data on the Ethernet card. Oh no, gotta do that now. And so this is where we were struggling yesterday, is to get this data off the interrupt controller, we have to ask the PCI config, like, hey, where is this line hooked up? I'm not really sure how he knows the PCI bus. I don't know how PCI knows which interrupt number it is, but we'll kind of gloss over that for now and just assume that there's some way. I think maybe initialized by the BIOS is what I was reading, but I'm not sure. So we were asking him where the interrupt was, and we couldn't get the interrupt to fire. But we could get that mechanism of just polling him, just saying like, are you done? Are you done? Are you done? With this little loop here. That was working. And so we knew that like the card was transmitting our packet in some way, but we were struggling to have it notify us when it's done. And I did just find the answer here. So what we expect to see is like, here I like register an interrupt handler. And here I expect him to tell me when it's done. So here I should say like transmission complete. And when I run this, I do see like some stuff happen, but that transmission complete is not happening at the right time. That transmission complete is actually happening when I type into this window, because I was getting the wrong number. So I should really see that like when I see the transmission okay thing happen before. And what I found, offline, saying we there is a little deceiving. One sec. So when I asked the PCI controller, what interrupt line are you? There's actually two fields here. One of these is interrupt pin, and one of these is interrupt line. And I was just reading the wrong one, and that was like, I just didn't notice that until I was reading again off stream. So interrupt line specifies which input of system interrupt controllers the device's interrupt pin is connected and is implemented by the device that makes use of an interrupt pin. This corresponds to the PIC IRQ number 0 to 15. And a value of FF defines no connection. So these like 0 to 15, this is what I thought was right. But I think this is what I was reading before. Or maybe I was reading interrupt pin, which specifies the interrupt pin the device uses, where a value of 0x1 is int A and B and C and D. So let's double check which one I was reading before. I don't know which one I was looking at, but whichever one I was looking at was the wrong one. So I was looking at 8 bits shifted. So I was looking at interrupt pin, and I should have been looking at interrupt line. Easy peasy. So if I just change that 8 to a 0 to do 0-bit shift, cargo run, I get an assertion that IRQ num is wrong. So let's just double check what's going on here. Right, so these IRQs, they're actually daisy chained through these like 2 PICs. How do I say this? This is like, where's my razor? This guy. They're actually daisy chained through 2 of these guys, because each interrupt controller can only handle 8 interrupts, so they kind of come in like this. And so when I set this up, said you can these interrupt numbers, you can tell us which one of these you're connected to, 1 or 2. It turns out that like most software doesn't actually care about this, so I'll probably turn this into just only looking at one, like reviewing both of the daisy chained PICs as like one thing externally. But it just means that if my interrupt number is greater than 8, I need to go to PIC 2 instead of PIC 1. So let's say IRQ ID is, what do we say here? This is if IRQ num is greater than or equal to 8, or less than 8, let's say. If it's less than 8, we go PIC 1. Else we go PIC 2 and we subtract 8. And we should assert that IRQnum is less than 16. And in reality, asserting here is like fucked. We shouldn't do that because our kernel will crash if like a device has bad IO, and that's like a bad reason to crash your kernel. But this is just for like debugging purposes for now, and later we'll we'll replace these with like proper errors and stuff. Okay, so here we pass in IRQ ID, and if what I checked yesterday is true, yeah, we do in fact start to see transmission complete, specifically when before we see the transmission OK flag. Now, what I don't understand is why the hell this starts like going bonkers badonkers here. It starts just like printing random memory. I think it's something to do with like a bug in my interrupt handling in general, especially when like they're getting fired like rapid. But I was reading on the page for this network card that I have to reset the buffer. When you handle an interrupt, you have to write the bit corresponding to the interrupt to reset it. Otherwise, we just keep firing the same interrupt over and over and over and over. So here I just need to tell this guy, hey, shut the fuck up for a second. I got it. So this is, I take the base memory and offset by 0x3e. And then I need to do a volatile write, because this is something that like might be volatile memory. Or maybe it's volatile write, I don't remember. And then here, let's just let base equals mmap range.start or something. And this has to come after we get the mapped memory. This needs to be moved, so that this is a static function, and this is unsafe. And I think we're chilling. Cargo check. And so now what I expect to see is I expect to see only a single log of transmission complete. And we did not do that right. So let's, how do I, oh no, reset. Oh, I need to read and write it. Oops. Oh, sorry. The last piece here is that, well, first I do, in fact, need to read it, they said. And here, let's just double check. We need to make sure that this read is in fact working. So we need to make sure that our read is doing an assembly instruction that's reading the right amount of memory, or else the card gets angry at us and doesn't work correctly. So this is register 03E, the interrupt status register. And this is a 16-bit register, it looks like, from this guy. So we can cast this to a base add 0x3E as mute U16, because it's 16 bits. And then here we do replace this with reg. Cargo run. And here we do see what we want now. So now we see we pulled the transmission OK flag once. It was no bueno. And then we got this like transmission complete, and then it's true here. So we are now have interrupts hooked up, which is sick. So this is at around like 1350 in the stream. So now we want to set up receiving of data, which I think might already be set up because we've initialized our read buffer. So maybe let's set up loopback mode first and see if we set up loopback mode, does it work? But actually, there's probably some cleanup we have to do here. We kind of left this in like a really shitty state. I think that maybe we should finish up this like transmission stuff and like make it readable instead of just like random pointer writes everywhere with random numbers, and work backwards from there. So here we've reset the device, we init the receive buffer, and now we want to do like init interrupts probably. With this guy. Probably. That seems reasonable to me. And is there anything in here that we need to check? So to initialize interrupts, unsafe function, init, what did I call it? Init interrupts? Yeah. And this takes in the base pointer. And it must also take in the interrupts handler. Interrupt, what do I call it? Interrupt handlers. Is interrupt handler data. Okay, and so what does he do here? We just copy paste this function that we wrote up here. Like this. Womp womp. And here we pass in interrupt handlers. Okay. Now we need to request the IRQ ID from the PCI bus. So that has to be in here. So we also need to pass in the RTL device, which is a generic PCI device, I think is what it's called. Does he not like that? Well, we'll get there later. So let's figure out this like IRQ parsing, which is like this. Oh, we also need PCI. Bang, dang, this is getting crazy. PCI and mute PCI. Okay. So he takes in PCI and RTL device. And this is general PCI device. Sorry, not generic. So this should be here we have general PCI device. And we also have to add this to the imports or else it doesn't like it. And now what doesn't he like here? We need to borrow this. And cargo run to see, I think all of that should still work. So we do still in fact get the interrupt. We're chilling. Cool. Okay, what's next? Sorry. Here we also have to set the interrupt masks. So this also belongs as part of init interrupts. Like this, and this is base cargo run. Ooh, what the hell? Oh, only this is initializing the LMR. This is setting up the transmission buffer. It's already easy to get lost here. Okay. So let's kind of walk through this and try to like clean it up and make it understandable for both me and you guys. So what's happening here? Base add 0x3c write volatile 5. Like what the fuck am I doing? Probably I'm just copying what they did here. Yeah, and so let's actually like pull up on the datasheet and see what the fuck they're doing. So they were writing to hex 3c, which is the interrupt mask register. So let's start by pulling out a constant for that. Interrupt mask offset 3c. And let interrupt mask reg equals base dot add interrupt mask offset as a mute 16. Okay, so that's step 1. And then here we say interrupt mask reg to volatile right, like this. So what's he pissed about now? For semicolon probably. Nice. And what is this guy doing? He is initializing or set interrupt unmask, or yeah, set interrupt mask, we'll call it. And for now, we'll just do this. And sorry, this will be a pointer. cut this, put this here, and we'll say set interrupt mask, and this it takes in base. Now, what's happening here? The interrupt mask register has these options for us. We can set interrupt on OK, error, transmit, receive OK, receive error, transmit OK, transmit error. And 0x5, I assume, is like some subset of these. Well, it is. I assume they're so stupid. It's some subset of these. So let's figure out what those are. My hex to binary in my head is like shit. And so every time I have to look it up. So we have 5. So we have print me as Boolean. And what is 5 in Boolean? 101. Yeah, so that makes sense. So they've disabled they're saying receive okay and transmit okay. Really, I feel like you should allow us, like we should allow all interrupts. But that's fine. And really we shouldn't do, like for now we'll just allow transmit and receive okay. So, transmit okay bit 3, receive okay bit 0. So this is 0 and 2. So bit 2 to the 2 is 4 plus 1. Yeah, okay. Sure. Yeah, we'll do this. There we go. There we go. 16-bit register. I guess we don't have to comment that. It's pretty clear if we're doing as mute 16 that it is a 16-bit register. Okay. We're chilling. So really, we shouldn't set the interrupt mask until we've registered the interrupt handler, or else we'll get interrupts that we cannot handle, theoretically. Like if it like happens to fire something. And oh, I guess they won't be unmasked until that point, so it doesn't actually matter. But I think that this is a better order anyways. And now we have a function to get the IRQ ID. This seems like a good like little chunk of work. So unsave function get IRQ ID, and this takes in the PCI device, or the PCI like configuration mechanism. It also takes in the RTL device, which is a general PCI device, and it returns an IRQ ID. I'm also looking at this and seeing that we can use general PCI device as non-mutable, and I think that's a mistake because this guy is like doing a sequence of operations on these guys, and we don't want those. We don't want like somebody else doing conflicting operations. So just while I'm in the area, I think that these guys should be all set to mutable. And we're just gonna do all of these guys. We're gonna say anywhere where you said and self, say and mute self, and mute self. That will almost certainly stop compiling now because someone didn't declare him as mutable. But first we need to fix this before that. So we can just take this out. This now needs to be taken as mute. This now needs to be taken as mute. This now needs to be taken as mute. And this now needs to be mutable. Cargo check. We're close. Self cannot be borrowed as mutable, blah, 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 blah. So PCI 106, more mutable problems. And the other one was in 131 and 106. So 131, he's got the same problem where this has to be mutable. Cargo check, see if it's compiles. And I'm actually kind of surprised it does. I thought it was going to have to be more problems than that. Okay, so I'm just gonna restructure this to do. So the first thing we did was test interrupts, and we finished that 1550. And now we want to like clean up this mess. Clean up our mess. Okay. So now we have here we can just pass in get RQ ID and pass in PCI and RTL device like this. And now this chunk of code disappears, and by disappears I mean move somewhere else. And now this feels a lot more reasonable. Cargo format, see how he likes this guy set up. And this feels a lot better. Maybe this gets it's kind of hidden in there. That's a function call, so we'll just say IRQ ID is this outside, and then we'll pass in IRQ ID this way. I think that's fine. This stuff is going to change later. No, it's not. Let's make a function for that as well. So this is clear interrupt. And in reality, I don't actually think this is how we should handle this, because he's just like raw writing a 0x5 there. So he's saying like, yeah, if you were read, sure, yeah, I got you. And if you were write, I also got you. But for now, let's just kind of do this, and we'll come back to this when we're actually trying to handle reads and writes a little bit. Like we're trying to actually do something with them. So here we'll just take in base again as a mute U8, which is like the where we write to get the memory mapped IO to this device. And let's just take this guy, shove him in here. And here we say clear interrupt base. And so here 0x3 is the interrupt status register. And do I have this anywhere? So no, interrupt status offset is 0x3e. Right, so that's this guy here. And we have to write these OKs to clear. So this is another 16-bit register, which we handle here. And we can call this, instead of here, we say interrupt status offset. We read and write, and we say, according to the OS dev wiki, we need to both read and write the register to prevent to clear the interrupt. Sure. Works for me. So now this guy's pretty clean. He's just registering the interrupt handler, setting interrupt mask. And now we cargo run. And we still see everything working the way we want it to. So I'd say our mess is cleaned up for interrupt handling. So this was like 2805-ish. Okay. So now what would be nice is to do like an interrupt, like a loopback test. So we want to see that when we transmit, we want to also see a receive. So how do we do that? Let's enable loopback mode on this guy, which, if I understand correctly, just means that things I write will come back in and trigger all of the hardware that's related to that. So let's look up loopback. Loopback mode is normally used to verify the logic operations of the Ethernet cable functioning correctly. In loopback mode, for 100 megabit per second, the thing takes frames from the transmit descriptor and transmits them into the internal twistor logic, which I assume means he comes back. Or else it wouldn't be called loopback, right? So here we need to set up our transmit configuration register and just enable loopback mode, which is bits 17 and 18. So here in our shit show here in our initialization where we're doing some testing, we take some data, we find the data pointer that we want to tell the Ethernet driver about. So the Ethernet driver has this register where we say like, here's a memory address, use that data. And so we put that in there, I think. Transmit data. What the fuck? Yeah, and then here we unmask something to enable transmission. And here we tell the Ethernet card about what we want to transmit. So we find its initial config, and then we set these bits are like set the length of the data. So I've given you a pointer, some data, but like how far do you want to write onto the network? This much. And then this bit 13 is a way to say like, driver, please start transmitting what's in there. So when it finishes, it sets that bit to 1, and then you go like 3, 2, 1, go, and it's time to go now. And so now if we're saying that we want to set loopback mode, I think that's just part of the same thing. Let's double check. Transmit configuration register. I don't know if this is the same one as this other transmission configuration. 040. So this is different. So what I was writing to was 010H, which is the transmit status register, which is a configuration for like each individual send. But it looks like there's like a global configuration that we actually want to set. So we can just set that up here. So mmap range start add 0x40 read volatile. So we get the initial state. Let global transmission config is this, and we make this mutable so we can like modify it. Let's print out initial transmission config, and that's this guy. This. And I'll just print him for now. We'll switch these to debug logs later. And then what we want to do is we want to set this like specific bit on him, or set these bits. So this is bits 17 and 18. So we say shift it by 17, and we want to write 2 bits, 17 and 18. And the value we're going to write is 0B11. And that's this guy here to set him into loopback mode. And there we go. So now, in theory, we should get a second interrupt that tells us that there's like reads to be done. So let's see. He didn't like that because this guy is a U8, so I always forget that I have to take this like pointer to a single byte and turn him into a pointer to whatever size we're working with. So this is 32 bits. And we'll say let global transmission config register is this guy. And then we can use this guy directly. So this is like this. And we also forgot to set him after. So here we need to say write volatile, because hardware might be changing the values underneath us, and we don't want Rust's compiler to like be doing some crazy shit with some optimizations, assuming that nobody else is writing this memory. And here we just say write the modified value that we just did here. He's complaining about some parentheses, so shut up, please, thank you. And we cargo run. And nothing crashed, but we don't see that like second read like I thought. So how now, it would be nice to have some sort of proof that this is working the way we want it to. The loopback function must be independent of the link state. So I guess let's see if QEMU's virtualization actually supports this. So RTL 8139 loopback. Because it would be possible that QEMU just doesn't support this. So there is a patch here which can detect reentry and return early. But it does seem like the driver supports it. So let's look at the QEMU source code. I think I have it pulled somewhere. And let's look at the RTL 8139 driver. And so they do have loopback. And they do say if we have loopback, then we do a receive. And they do, in fact, have this debug print. So what would be kind of cool is if we could enable debug printing in QEMU and see that log. QEMU debug printing. Some guy in conflicts dtrace. Okay. So I guess probably dprintf. Let's look him up. Dprintf. And look up he's a define, and he probably looks at this guy. If debug kv, oh, is this defined per file? Network stuff. Yes, network stuff. It's fun though. It's fun. This dprintf is only, it's not runtime enableable. So it's hard to prove that this is working. But we can start trying to like read the network card's receiving buffer and see if after we write, do we get something? Because hopefully we do. And so somewhere here, okay. So here they're saying that I need to tell it that I accept stuff. So that makes sense that I'm not seeing any interrupts fired on the receive side. Because I haven't done anything to initialize that. So let's come in here and we'll say, we'll call this enable loopback untested, and we'll say that this was done at around 36 minutes into stream. And now we have to configure receive data, and then after that we'll be able to test send receive loop. Okay. Okay. So let's try this like receive stuff. So what's happening here? We can tell it whether or not we can accept broadcast, blah, blah, blah. Let's just read the official docs because I don't really trust this wiki as much as I just trust the datasheet, but I also don't trust the datasheet because datasheets lie. And sometimes the wiki says that the datasheet lies, and so that's also useful information. We gotta read both. So this is 044H, I think is what they said. Receive configuration register. Okay. And they said that we should be accepting all packets. So 1 shifted 7 is the wrap bit. And Xerix F is AB, A unit. Okay, let's just see. So they're saying they want me to look at bit 7. Wrap. When set to 0, RTL will transfer the rest of the packet data into the beginning of the RX buffer. This packet has not been completely moved to the RX buffer, and the transfer is received at the end of the RX buffer. When set to 1, we'll keep moving the rest of the packet data into memory immediately after the end of the RX buffer. If this packet... Oh. So I definitely want wrap. Going past the end of the buffer is crazy. That's a crazy behavior to support. Because that's just going to like write like something. I guess if you had like infinite RAM, you could just like transmit forever. Yeah, so definitely we want wrap. And these guys are this. So this is kind of weird to me. If I have like accept all packets set to 1, and then I say accept multipass packets set to 0, how can this be true? I don't know. But let's just ignore that for now, and we'll just do what the OCF wiki says. It seems reasonable if I'm just like, hey, accept anything, fuck it, I don't care. That is the case that I'm in because I don't even have Ethernet frames right now. I'm just like writing like random crap to the buffer, and so I really do just need to accept literally everything in the world. So I'll set bits 1 through 5 because when set to 1, all packets with the CRCR will be accepted. Yeah, I want like literally everything. Because my packet is definitely malformed. So we'll set bits 0 to 5 and 7. 6 is reserved. So here we just need to do this. So this is a set up receiver configuration, global. And this was let global receive config reg is the memory mapped region of our PCI device, offset by 0x44, I think is what they said. 0x44. Yep, that's right. And this is a 32-bit buffer, I think. Let's just double check. So in the datasheet, we have 32 bits. So this is, in fact, a 32-bit buffer. Then we want to get the current value. If I was smart enough, I would just initialize this to all the things that I want. But since I don't want to just like fuck stuff up that I don't understand yet, I'm starting with the default state and then adding on what I want. So this is this guy, read volatile. Let's take a look in there. And we can say initial receive config just for the purposes of learning. This would also be hex printed because these are bit masks and stuff. Print is wrong. These should both also be print lines. And here we say global receive config. This. And now let's set the bits we want. So we want set bits. We wanted all 5 of the bottom ones. So that's 0x1f. Oh, this is 6. 1, 2, 3, 4, 5, 6. So that's a 3f. So this is the 6 bits and 0x3f. I guess really I could just say like 1s and let it figure out the rest from there because it'll mask out the parts that are important. But let's be a little bit more precise. And then we also want to set the wrap bit. So that's bit 7. And this is a single bit. Okay. Now we write that back to the device, which is like this. And we're chilling. So let's just say what we're doing here. Accept every packet that ever existed. And overwrite start of buffer when too much data. Wrap, baby. Okay. So now, was there anything else that they say I have to do? No. Sure. Let's just try it. Cargo, run. So I still don't see myself firing the interrupt twice. But I wonder if there's a way to poll for the receive. So it sets the RE and T bits high. Did I already do that? Enable transmit receive. I guess we should do this after we set up configuration. I still only see this guy written once. Or the interrupt firing once. So let's start going into like polling and see if that helps. Or you could argue that maybe the like default state of this guy has some stuff in here that I don't actually want. So let's just try writing him raw without reading from first. So we'll do this. Start him with 0. I still only see 1 interrupt firing. But you could argue that it's because I wrote if like both the read and write come in instantaneously in a single interrupt, maybe that is causing problems. Like, sorry, not problems. Maybe that means that like the interrupt only fires once, even though 2 actions have happened. So let's actually look at the status register before and after the interrupt. So let's print out the status register, I don't know, like here, before we transmit anything. So we'll say let status reg val is equal to map range start, and we need the interrupt status register, which is offset 0x3e. And this is a 16-bit register. And we'll read volatile, and we'll print him. So we'll say print line in hex status reg val. And we'll just copy paste this code into the interrupt handler as well. And we'll see what happens. He doesn't like this because this is not a proper thing. So before the interrupt fired, there was nothing in the status register, and now there was 0x4 in the status register. So, which is this, only transmit. Okay, so we didn't receive anything according to this. Fuck. Okay, but maybe we can like look at the receive buffer at all, and maybe we can just poll to see if we get anything. So early RX status register, but is there like a normal RX status register? Config register here. What is early RX? Early, so that's 034. 030H? Why are these not working? Receive buffer. Maybe it's in the table of contents. So receive status register in RX packet header. Early RX status register. So these are just like at the beginning of chapter 5. Okay. So I guess I can just poll this and see what we see. Because maybe the interrupt only fires if like we get a valid packet, which we're definitely not sending. But this is in the RX packet header. And it's like, where do I get this RX packet header from? Early RX status register. The power on value is 0. It is set when RX byte count on the receiving packet exceeds the RX threshold. After the whole packet is received, we'll set ROK and RR and ISR and keep this bit simultaneously. Setting this bit will invoke an ROK interrupt. So that's interesting. This bit... Oh, this is only readable, so we can't set this. So saying setting this bit is kind of funny because we can't. This bit is set when the local address pointer is equal to sock capper. In the early mode, this is different for the buffer overflow, blah, blah, blah. Early RX bad packet. This bit is set whenever a packet is completely received and the packet is bad. Writing a one-to-list packet will clear it. Read, write, read. Not writable. But they're claiming that if I write it. So maybe you can write to this and they're just lying to me. Maybe. But let's look at this register because this will give us a bunch of useful info. So here, let's just print line. What do we get from this guy? So this is a 8-bit register. So we have base, our mmap, range, start, add, 0x36, read, volatile. Let's see what's in there. Cargo run. What we got, baby? 0. So none of these are set. I think. This bit is set whenever a packet is completely received and the other packet bad. Okay, so we're missing something, right? We have like no confirmation at all that we're receiving anything of value. So I think what makes sense here is probably to start making this shit a little more readable so that it's easier to debug. Right now, I'm just like looking at this and my brain's like exploding. Like I don't really understand what I'm looking at all. So let's try to like break this up a little bit. And while we're in the process, we can like read through this again and hope that we didn't miss anything. Okay. So let's enable loopback. And we'll say debugging. And we'll just split the function out here, I guess. First, enable loopback takes in the base address, which is a mute u8, and just does this shit. And this takes in mmap range start. And this says base.add. And this is unsafe. Cargo check. Cargo run. Okay, nothing crazy here. So now we can just move this function out here. And while we're here, let's look closely at what's happening. So base.add 0x40, and this is the transmit configuration register. So we'll say const transmit config offset is 0x40. And here we'll say transmit config offset. Now we have a name. And we'll call this transmit config reg. Okay. Now we read the config, which we don't have to name so great like long anymore because we're in like our own little scoped area. And we see what we is, we set our bits, and we write volatile. So let's double check here that we wrote it. So written. And then let's do another check here. Read back. And let's make sure that this is in fact what we wrote. Okay, so these are initial transmission config, written transmission config. That's what we're looking for. So here we're looking to see that bits 17 and 18 are set. So this is, I guess what we should do is shift this right by 17 to confirm. And so the initial so this is a problem, right? Our read back transmission config is not what we wrote. So why the fuck not, right? And this is probably part of the problem. So we should double check that the bit set is correct. So if we set bit 1, we want to shift by 1. So if we're setting bit 17, we want to shift by 17. That seems reasonable to me. And maybe it's because I'm actually setting these like read-only values. So maybe I do actually, unfortunately, have to maybe mask out the read-only values or something, or else maybe it rejects the write. Maybe. So let's try, instead of writing what we got, let's just try writing this directly. So we can say this equals 0 temporarily. And so now we're saying that we want to write 11, and we're getting back this big ass number, 11 binary. So still something's not right. Maybe QEMU loopback is not enabled by default. So let's see here. In the QEMU driver, is there some sort of like compiled out configuration or runtime configuration that we're missing here? So let's see. Well, they have txconfig, so that's 0x40. Does that match what we're writing in our driver? In our driver, we are writing 0x40, so that's a good clue. txconfig bits, loopback is 1 shifted left by 18 and 1 shifted left by 17, so that is in fact what we're writing. Loopback, 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 loopback. Right, we're setting this. Oh, oops, this should be, I thought these were like this. Sorry, one sec. Let me double check. Let me double check that what I said before was correct. Yeah, we're still not getting back what we want. And let's see. Okay. So they do support loopback, but maybe they don't support writing the loopback. Maybe. So let's look at where txconfig is used. If the transmitter is not enabled, we're not allowed to write. Aha! Okay, so that means here that when we enable transmit receive, this actually has to come before loopback enable, or else according to this QEMU implementation, it won't work, assuming this is the right thing. So RTL transmitter enabled is chip command state and T command TX enable. So this is 0x04. So somewhere we set command state on chip command write. And chip command is 0x37. So yeah, here they are saying that this 0x37 that we're running here needs to happen to enable the chip. Okay. So now I still don't see anything too interesting happening. But, okay, sweet. This redback transmission config is now what we wrote, which is like a big win for us. We're happy with that. So we'll say here, maybe we like assert or yeah, let's just assert for now and we'll turn this into an error later. That the written config is what we wanted. So we'll say new val and written and the config value that we wrote. That way, what we should be able to do is we should be able to move this around and see if what our write applied. And you can maybe argue that it's a program error, or you could argue that it's a device error. So let's actually say it's a fix me, because if it's a device error, then like we shouldn't crash, but we also shouldn't like continue trying to use this device. And so what we should probably do is like return an error here and fail to instantiate the driver. Like this. Okay. So if I run this, we shouldn't crash. Good. And if I move this back before we enable transmit receive, we should crash. Sick. That's really solid. Okay. Now let's just clean up this logging a little bit. So we'll say initial transmission config, written transmission config, and read back transmission config like this. Cool. Cool. So now let's make a function for this as well, because I'm going to forget what this does. So we'll say enable transmit receive. And this is relative to the base address of the memory mapped device. And we just write this value in memory. When we want to do that. So first, let's double check what this register is supposed to be after we call this function. Okay, so 0x37. Do I have a 0x37 in here? We do. Command register offset. And where else is this used? In reset device. So in reality, we should probably read the device before we write it. So say let current, reg equals this. And we should double check the type of this. So this is command register. What am I doing? Searching that is not what I want. I want what is it? 0ch. Oh no, I want the, sorry, that's what I'm writing here. I want to see what the value of this is. This is 37. So this is an 8-bit register. And we want to use its current value, which is let val equals reg dot read volatile. And then we say val, we adjust this bit mask. So val dot set bit 2 and 3. So this is shift by 2 bits, 0B11. And then we say reg write volatile. Am I losing my mind? Write the value. Jesus. And now we read the value of that. So we say let set val equals reg read volatile. Read back, and we'll say assert eq val and read back for now. Fix me. Return error. Okay, so we don't assert, we run. Very cool. And so now we can say that we've like enabled transmit receive. Bump, 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 bump. So why isn't this working still? So we enable loopback. We see that it is indeed set. And now we need to set up our receive register. So let's init receive configuration. And this is init receive configuration like this. And let's just like copy paste all this shit in here. And let's start stubbing out his argument. So he takes a mute U8 as the input, the base of our memory mapped device, which is this range here, start. And he starts using this guy. So 0x44 is the receive config offset. And we read his state. We set our bits. We write our bits, and we now do the same check. So we say let set val is him read again. And assert that the set value is what we wanted. And while we're here, let's double check. So accept every packet that ever existed and global receive. So this is on, oh, it's fine. It's fine. Global receive config. Cargo run, and let's just double check. So no assertions, we're good again. And now let's double check what we said here. So we said receive config offset. So when we set the receive buffer size, are we overwriting what we wrote before? Let's double check that this is in the right order. No, we are not. Okay, so let's cut and paste this guy up here. Like this. Cargo run. Everything still compiles, everything still runs. And now I guess we just got to start getting into the nitty-gritty. So we know that these are in fact the same. So the write applied. And so now the question is, why is our data not making it back to us? Okay, So is there anything interesting happening here? Here we set status reg val. Let's say status reg in init, so I know what the hell this is. We set up some data. We stick that data into the transmission data pointer, and then we set up our transmission config for this transmission, and we write it. And maybe we haven't waited long enough, so maybe we need to look at this early status register and just we'll loop and we'll print, and we'll say if our early RX, if it's completely unset, 0, 1, 2, and 3 are all unset, we haven't received anything yet. So we'll take this, we'll say get bits, no, we want 4 bits. And if val is not equal 0, we break. But not before we print, baby. And so we are just like spamming zeros here forever. We never ever receive the buffer. So why? Why? Yeah, we gotta find a way to like debug this a little further. Maybe we do just have to send a valid Ethernet frame. Let's double check our init receive configuration, which is 0x44. So early RX threshold bits. These are to select the RX threshold multiplier of the whole packet that is transmitted to the system. Buffer in early mode when the frame protocol is under. Oh, in early mode. Maybe I haven't set early mode. What the hell is early mode? Won't be used to transfer data in early mode. So maybe I'm just reading the wrong register. Maybe that early mode register is not a valid thing for me to be looking at. Receive status register. Packet header. Like, what the hell? Oh, maybe this is in the buffer. RTL 8139 RX status register. Maybe somebody on the internet will have like a clue for me. RX header. All received packets are stored in the RX, including RX header and 4-byte CRC. Okay, so what we can actually do is we could look at the receive buffer. So where do we set up receive here? Init receive buffer, and he returns a box U8, which I've dropped immediately, by the way. That's fucked. Receive buff is this. And really, we actually need this to be an unsafe cell because memory writes could happen in between us. Let's see, is unsafe cell rust volatile? Is this true? I guess I could convert it into a pointer and do a volatile read if I really have to, which is probably what I should do. So down here, we'll look at the RX header. So first we'll say print before receive. So we'll say let RX pointer is a receive buff as mute pointer, and we'll look at the RX pointer header. because this is the first thing in here. So let's look at that again. Because maybe early receive isn't good, but the header that gets pumped into the beginning of our buffer, maybe that's valid. So this is 16 bits. And so we do rx pointer volatile read. And let's just print line this guy in hex. And we should probably do this before we start transmitting. So we'll start here. And then we'll do this, rx pointer. Cargo. And maybe we don't do this in a loop yet. We just see what the value is and see if it changed before and after. Oh my god, you're such a whiner. There we go. Mute. Okay, so we have rx pointer 0x1 here. And why don't I see an rx pointer before? Rx pointer. Oh, because I didn't write it here. Rx pointer. So we do have a 0 that's turned into a 1. So that's a really good sign. We have like some proof that something fucking happened. And where does this go? I guess what happens is mute the compiler, lol. Yeah, dude. I sometimes like I love it when it tells me I did stuff wrong, but sometimes just like I just want to do the wrong thing. Let me be wrong. Okay. So we have this receive, okay. And so how do I know like how much data I received? How am I supposed to work with this receive buffer? Transmitting packets. Use a round robin style for transmitting, sure. After performing a reset, I get this part already. Where's the like receive part though? Do I need to like set a new receive buffer every time? That doesn't sound right. I guess maybe I just have to like remember where I read up to before and keep track. So probably somewhere in the header, they must tell me how long it is, right? They have to. They have to. RB start, early receive. So I'm not using early, I guess, because I don't see any evidence that that's happening. I have this configuration register. But I don't really see anything about like received packet lengths or jumping through multiple receives. And there's no like length in here. This is all just bits. So maybe what they assume is that since I get a valid Ethernet frame, I can use that Ethernet frame to tell me about the length of my packet. But because I don't have that, it's fucked. So here I have a frame alignment error. What does that mean? Frame, I think that's what I saw written. I saw rx pointer header says 0x1. Frame alignment error. What does that mean? Frame alignment error. Sure, it's damaged as fuck. Yeah, I get that. It also triggers a frame check sequence. I wonder if I still get the data, though. That would be cool. And maybe what we can do is we can look at what like a frame alignment error even is here. So here they write the buffer and they just set it to val. But where do they like... Shouldn't shouldn't the buffer have to be like incremented after that at some point? Let's see if they have that like wrap bit thing. So I don't see that used anywhere, which is kind of odd. I would think that this would define something about like where I'm writing to. All of these aren't really used. surprisingly. Unless they pass them into some helper function in another file, maybe. So rx config bits. This isn't used anywhere. Am I crazy? I must be. Tx config bits also not used. Tx loopback. This is used. So what am I missing? Like none of these are used. What is the rx config? Rx buff pointer and Rx buff adder. Why are those two different things? 3A and 3.8. 03AH. Current buffer address. Oh, okay. That's interesting. Current address of packet read. Current buffer address. So maybe when I receive a packet, I look at this. 38H. Doesn't really ever talk about it. But let's look at those and maybe they'll tell us something. I'm surprised that I can't find documentation about this in here. Maybe it's called something else. Receive configuration. Is there anything in here that's just like how the fuck you're supposed to use this thing? Functional description, receive operation. Let's look at that. Maybe that'll give me some clues. That's on page 47. 47. The incoming packet is placed in the RX FIFO. Currently, it performs address filtering of multicast packets according to hash algorithms. When the amount of data is level defined in the received configuration, it requests the PCI bus to begin transferring data in the RX buffer to the PCI bus master mode. Not helpful. Okay, let's look up like the names of these registers again. Maybe looking up their addresses is not what they have them defined in here. So let's look at CAPR. Capper. And what about packet underline? What about CBR? Nothing. I guess maybe I can just start like, let's just read a bunch of memory from here and see if I see anything that resembles what I wrote. So I tried to write 0 25 times. Let's just try to write like 1, 2, 3, 4, 5, 6, 7, 8, 9, and see if like I can find that anywhere. So nothing in here is going crazy. And let's see if it like still dumped that info in there, even though it knows it's wrong. So let's start by just like, I guess we should look at this current address and current buffer address and see if those correspond with anything. So these are offsets 3.7 and 3.8. Oh, sorry, 3.8 and 3A. So what is this called? CAPR is mmap range start add 0x338. Yep, as a U16. Read volatile. And then we have CBR, which is 3A, as a U16. And let's read both these and see if they are interesting in any way. Like this. And I guess we also want the RX pointer. Right, because if these are not the same, that means that we've like advanced the pointer by running this. So this should be RX pointer is RX pointer. Cargo run. Let's see what we get. Okay, so we see that the RX pointer is this, and our capper is really high, and our current buffer pointer is 44 in. So let's try now if we reduce the length of this. the data we're sending. Do these numbers change? No. Interesting. Let's just read a bunch of the Rx pointer. Hi, Kaplan. Yeah. Okay. Let's look at this receive pointer. And we know that the header is in the first 16 bits. So we can maybe assume that the next 16 bits would be data. Maybe. So let's add 1. Because it's in this U16 space. We'll read volatile. And we'll call this Rx pointer plus 1 is this. Like this or something. Let's see what we get. Does it resemble anything interesting? 0x40. I mean, it's not 0. 2, 3, 4, 5. 2, 3, 4, 5. 2, 3, 4, 5. Okay. Let's get a few bytes out of here. Oh? We're seeing a 1 and a 2 in there? Let's put a bigger number in and see if that changes. Oh, oops. This 0 and 1 maybe. Oh, okay. So there's definitely something promising in here where we are definitely seeing some of the data I wrote come back. Now, I don't understand why it's coming back every other byte. That's fucking weird. But maybe it's in there. Definitely in there. So that's a really good sign. So we'll say we're debugging debugging received data. So if we can extract this 1, 2, 3, 4, 5 back, or 0, 1, 2, 3, 4 back from this guy, we're gonna have like a really good idea. We'll have like some confirmation that we have any clue what's the fuck is going on here. So how do we want to do this? Rx pointer. Let's double check this like U16 shit isn't causing problems. So we'll go back to it as a U8. And let's do this in a loop. So for I in 0 to 50 or something, we will print the pointer plus I, which is I. This will be plus I read volatile. Okay. So now it looks totally fucked. Before it felt like we were seeing something that resembled our data, but now we're not at all, which is odd. So what happened? Oh, here's a 2 over here at offset 8. Maybe we'll try to write these all as 0xFF. And let's make sure this is a vec U8, which is from the alloc crate. Aha! Okay, so we're seeing some FFs in there. That's good. Let's make this a little bit longer. So we'll say 0xFF, and we'll write this like, 120 times or something. And we should see like a chunk of 0xFF. Okay. So we are seeing these 0xFFs like propagate through the memory. So even though our header says that we're fucked, that we didn't get the data right, it's still in there. And it looks like this offset 2 and 3 are probably the length of the packet. Because we see those changing. So here we can maybe infer from the data that the first 2 bytes are the 16-bit status register. Calling it a register is a little here. Header, right? These are 16 bits. And then maybe we can assume that the second 16 bits are little endian length. So let's take a look at that. So what we should do is we should say let length is rx pointer add 1 read volatile. And we can print line length. Length. There we go. And let's take a quick little peek here. And we see length is 124. Now the question is that what I wrote here? I wrote 120. Let's try something like 10 and see what we get back here. Do we get length is 64? So maybe there's like a minimum length or something. If I go above 64 though and say like 70, I do get 74. So I'm getting like 64 minimum and then like length plus n. Let's look at this CBR value, which is like the buffer pointer that we saw in the spec sheet. And let's print this as decimal. And if maybe we'll see him like incrementing at about the rate that we're seeing this guy at. So we're saying 74 and we're seeing a CBR of 80. Okay. So there's something here. There's definitely something where the length that we're getting in the receive buffer is related. Maybe it's because there's like a minimum length due to like Ethernet frame header. And we're like not filling that in correctly. So it's saying like, your data's invalid. Get fucked. And then maybe the second packet will come in at the next spot. So maybe that's like how much we're supposed to increment the pointer after or something. And there's like a minimum of 64. Spitballing. Not really sure. It seems odd to me that like I don't see that information in this datasheet. It seems like understanding how to fucking read the data is like a very, very, very important here. But maybe it's like a setting in this receive configuration register. Of the whole packet in early mode of frames process, blah, 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 blah. Maybe something in here tells us where it goes. We'll transfer the rest of the packets down. This is wrap. I don't care about wrap. Command register, configuration register 0. This is not anything related. LWake, memory mapping. Sure. Vital, power management, flow control. I think that's not related. I think that's like more like on the line shit. Long wake up, interrupt, transmit status, basic control, auto negotiation. Nothing in here that's too interesting to me yet. Auto negotiation. None of this is like how do I read the data, which is all I want, man. EEPROM contents. Don't care. Don't care. Status registers from PCI. Maybe these are useful in some way. Configuration-based functions. Parity errors. Why are these in PCI space? That's really odd, but okay. I would think that everything comes in through the IO mapped area. Power on state, power management. Come on, man. Something in here has got to tell me how to read the fucking data. This is so like, he's just like, I copied in there. Okay. Ooh. RX. I like the word RX. Continuously monitors the network and when reception is enabled. When activity is recognized, it starts to process the incoming data. After detecting receive activity on the line, it starts to process preamble bytes based on the mode of operation. He expects this frame to start with a simple paired JK on the first by the 8-byte preamble. checks the CRC bytes and checks if the packet data ends with the TR symbol pair. Okay. Control frame reception. Enters a back-off state period when it receives a valid pause packet with pause time in. Okay. I just want some clue on what I'm supposed to put on here. Pause packet. Is that the only mention of a pause packet? Control, pause, yeah, there's flow control, IEEE 8023 flow control. So I guess I probably just need to read more about what's supposed to go on here. Lots of reading to do. But I think I'm pretty, like, stoked that we have any read and write at all. And I think that I need to understand the data format a little bit better before I start pushing on, like, formalizing this driver in any way. We're still very much in, like, early probing. But I think that we can say that we did, in fact, get some sending and receiving working. Right? We have some, like, pretty good indications based off of the fact that we're, like, seeing our data in here, that we're like transmitting data and we're receiving it. Now, we don't understand why our receive interrupts aren't firing, but it's very likely that it's because the data is invalid, right? Because we actually have only enabled interrupts for where did I write this? Enable interrupts. Interrupts. Init interrupts. Yeah, here we go. Here we have only set the interrupt mask for bits 0 and 2. And actually, I wonder if we can set the interrupt mask for just like, fuck it, give me everything. And maybe we will start to see the second interrupt. We will start to see like a read interrupt occur. I do actually kind of look at that. So the interrupt mask offset is 3C. So let's look at 3CH here. And let's just set them all to 1. Fuck it. So we'll comment this out and write in 0xFF. Cargo run. And we still actually only trigger the interrupt one time. So there's still something missing there. We can't just say like, give me a transmission or an interrupt on everything. But I would think that we would get a receive error interrupt. Oh, let's somewhere we were pulling the status register. It would be nice to see this R error. That seems pretty reasonable. So let's go back and look for the status register in here. I only am using it for clear interrupt, but maybe I'm using 0x3E directly somewhere. Yeah, here I have the status reg val, which is what I was looking for. So here we'll say status reg, and we'll print him also down here somewhere before we do our transmission. And this is no longer basis and map range start. Okay, so our status register starts at 0x0 and then becomes 0x5. Which is actually 2 bits written, right? This is 5 is bits 2 and 1, I think. Okay. Okay, wait. That's actually huge. That's huge for us. So, if I disable loopback, I shouldn't see 0x5. I should see 0x4. Oh, okay. Let's go. Okay, that's fucking sick. So we are firing an interrupt on receive. It's just we're only getting one interrupt because both of those receive and transmit are happening at the same time. Okay, that's sick. Okay. I'm pretty happy with that for today. I have to do some more reading here to try to figure out what I'm supposed to drop into the Ethernet controller. Right, because it's clearly not just like any data, because I'm getting like invalid packets. And I also want to understand a little better like what this like receive header is supposed to be, and I just think I need to do some more reading to understand like the data and what's supposed to be coming in and all that thing. So I'm gonna call it there. I think we like accomplished enough today. Pretty happy with that. So thanks for tuning in. If you're watching on Twitch and you want to catch up, there's my YouTube is linked in my channel, and if you're watching on YouTube and you want to catch me live, talk to me, ask me questions, you can catch me most days at 2 Pacific. Thanks for tuning in. Catch you on the next one. Bye.